you have any questions. You're solving the x1 for t, and you're replacing the t in the y. And that should give you the rectangular equation. Try to keep track when you first see it go through of orientation, the direction of it. Put a little arrow in that direction. You know, and if you solved it a little bit differently than me, that's fine, as long as you came out with the same thing at the end. And again, this was a line. You tell me if you have any questions. Solve for t. Plug it in. Just fix it all up. Don't leave it to me like this. Don't leave this. Resolve that. Distribute it. Separate it, reduce it, whatever you need to do. Combine all terms. I'm looking for this as my final one.
Why did you give us?
Where are you?
The one right next to the one you just circled last.
Where did the 3 come from?
Yeah.
Oh, I made this one fraction.
Yeah.
So if you make this denominator 3, that has to be 3. I put it all over one fraction. Like, you really shouldn't leave it this way. You should make it one term.
Oh, 3 over 3.
Yeah, I just put it over a common denominator. Sorry.
No, it's okay.
I usually try to write the steps out this way it's not confusing looking. Rohan, you have your... Okay. So try to leave it as one term. I think this one we did in class, number 7. And this one we looked at on the homework, because I told you that's what you were going to be doing tonight's homework, last night's homework. On a radical, when you take the cube root, and you leave this as a cube root, it kind of looks a little strange that way. If you want to use your fraction rule, raised to the power over the radical part. Or if you left it like that for me, and that's fine. We're getting the same look that the other one had. As long as you're catching the concept of eliminating that parameter and making it into a rectangular. I think you really, really see it when we hit the ellipse, the circle. Then you really see it. A line, you're kind of like, it's a line, or whatever. So these are a little, I like these a little bit better because I think they're a little bit more seeable in this. And when you graph that, you can graph your ellipse and your parametric all in one swoop. And we don't graph functions with your regular y equals because you can never get an x with 2 different y's unless you put it in y1 and then y2. So parametrics allow you to do that also.
So did the 2 theta have any effect?
None at all, because it's still just an angle.
Okay.
Because you can do cosine, sine squared. So technically I should have said this. It's still an angle. It still has that property. Yeah, we'll bring this in 2. Let's put a 2 in here. Anna, again, don't leave this line. Resolve it into this one. Always collect your terms. Get rid of your parentheses if possible. And this guy gives you an ellipse. Now these you didn't have the night before. This one. You offset the center on this one. You want to leave this one over 1. It's absolutely fine. Over 1. Questions? Good. There's another ellipse, and then there's a hyperbola. The hyperbola is kind of nice too. That came with your other property, your other rule, your tangent one. Just divide everybody by cosine to get a secant. And here's a circle. Circle, you're going to take your basic parts and remember to plug them in. It's good here too because you get to see the coefficients when they're the same. Like when you start your ellipse and the coefficients are the same, there's your circle. So at the end, if you just multiply through, you'll get your circle formula. If you left it to me as that one, I'm not worried about that either. That's fine. No, because you're additive.
Can you go back up to 23?
Yeah. Thank you. We're good? That was it. That was it. Everybody okay with these? 23? 23, you were looking for a secant and a tangent. So when you start with this one, with your basic Pythagorean theorem, your Pythagorean identity, you need to get a secant. So if I divide this by a cosine squared, I'll get the secant. So divide all of these by cosine squared. That gives you that other one, the other identity. You don't have to memorize it. You just have to be able to get there. And that'll help you get through that one. Go backwards. Okay, now we start out with two components, a horizontal component and a vertical component. Anything that affects the horizontal, like wind speed, if you start a little bit away from something, if you move a little forward, anything horizontally affects the x. Anything vertically, you stand on a building, that's a vertical movement, it affects the y. This right here has to do with a gravitational pull. This is what brings your object back down. So it has to do with 32 something or others, but then there's a formula for it, so it always comes out like -16 squared. You have to remember to put this part in here, or your arrow, your ball, whatever, your rocket will not come back down. So we start very basic. We have a velocity, we have a t. T is your parameter, and then we're going to use an angle. Okay, so we're going to put our calculators in degrees. So if you get your calculator started in degrees and your mode in parametrics, you should be able to get that started. Now, an arrow is shot with a velocity of 205 feet per second, and you're going to always have to watch out if they give you feet per second and they give you yards as a measurement, or miles as a measurement, or minutes as a measurement. You're going to have to watch the conversions at an angle of elevation of 48 degrees. So here's your angle, your arrow being shot up, and it's got to come back down to the ground. Okay, we're going to find when and where the arrow strikes the ground. Now, before we did this, let's assume that we're going to launch it from here. We're going to shoot it from there. Before, when we did this, we could only do two things. We could only do time and a vertical height, or horizontal distance and vertical distance, but we could never do all three at the same time. With parametrics, your x is your horizontal distance. When the arrow hits the ground, I'll know how far away from, if I shot the arrow, I'll know how far away from me it hit the ground. I'll know how high it went. And my third parameter is time. Time is moving like this. This is time. This is how we measure time. So what we're going to do is fill these parts in. So your x is going to be your velocity, 205. T, don't forget your t. cosine of my angle. It's really kind of, it fits in the formula very, very nicely. Y is my velocity. My t, we had no wind speed, so that didn't have any effect here. My sine, and remember cosine always goes with the x, sine always goes with the y. And then we're going to bring it back down. It's kind of like your negative 16x squared when you're doing a parabola or a basic one. That's what it's going to look like. The hardest part is the window. Because we're gonna think this one through. This is an application. So what's the x and the y minimum? Could I have a negative x distance? Could I have a negative y distance? So what's my minimum for x and y? 0. Okay, so let's start like that. Put it in your calc. The first couple are going to be a little bit tougher, and then you'll get the hang of it. Don't forget your t. If you forget your t, it's not going to look the same. So put them both in. Okay, now, before we do that, we're going to set our window. We're going to try. My arrow to come up and hit the ground should take about how long? How long would you say if you shot an arrow? Would it?
Not very long.
Not very, so like what? 3 seconds? Let's make it like 0 to 10 seconds for now, if that's okay. And my t-step, when my time is small, should also be small. I'm going to play with your t-step in a minute, so right now leave it at 0.5. My s-min, this is my horizontal distance, has to start at 0. I'm really not sure how far he's going to shoot this. I can always go look at my table. But for now, I'm just going to put in 300. I really don't know how far away this is going to go, and we're going to look at your table in a minute. My y-min, 0, and how high up in the air do you think this would go? An arrow usually goes pretty high, it arcs pretty far. So like, give me a distance. 100, let's try 100. So you have to make sense out of this a little bit, and we'll go to the table and we'll see it ourselves. But we're going to look for this. Now, when this goes up and down, when it hits the ground, which one am I looking at, the x or the y, for it to be 0? The y. The x is always going to be increasing. It's a horizontal distance. It's never going to go backwards, right? Isn't my distance going to keep increasing? My y is going to go up, reach a maximum, and turn back down. My time is what we're going to trace all the way through this. So now let's hit graph and see what we have. Now, we're off on our table, on our graph. That's okay. Take a look at your table. Here's your 0. Bring up your 0. Let's look at your table. Your x is going to keep increasing. Your y is going to increase. I see it increasing. And look here. About 5 seconds, didn't it turn back down again? See it? So, I want to see how long does it take me to hit the ground. Between what seconds does it hit the ground? 9 to 10, right? Between 9 and 10, and we can tell because it had to hit the 0. Somewhere in here. So, I know I'm at least 10. Maybe I'll change my seconds to a little bit more. Look at your horizontal distance. Look how high that is. It went pretty far. We had no clue, but we can tell from here. So we could make our horizontal distance 1,500. My y, oh, look how high my y went before it turned. 360 something, right? So now let's go back to your window. Let's change this to 12 seconds. Our x max, let's make it 1,500 because it was 13 something. And this guy, what did we say, went to 6?
400.
400? Okay, so now, we want to see this parabola turn. This is what you want to get to. You want to be able to trace your parabola. you can always go to your table to see what your value should be. It's good to get a start, guesstimate. What I like the guesstimate part, because this way you're actually thinking about what your application is doing. Because the worst thing to do is just throw them in and have no clue what your application's doing. Now, watch when we hit the trace button. Hit the trace. Look at the three parameters: time, X, and Y. So we want to know when and where, two things. When and where will it hit the ground? When, how far away from me that I shot it, is when my Y is 0, and when, that's my time. So I'm going to trace this little thing. Notice your T-step. This T-step is incremented the way you incremented your T-step. Are you tracing? Trace? On your cow? Trace. You got to be with me here. Okay, this is your T-step on your cow. You don't want to put this too low, or this goes very, very slow. You don't want to put it too high, or you're going to be jumping around too far apart. So we're coming down. We want to get the closest before it hits the 0. So there I'm at 3. My Y is at 3 something. The next one down, I went below the ground. So I'm going to back it up, and I'm going to look right here. I'm very, very close. I have to, and remember, that in precalc, we need 3 decimal places. This is the tricky part. We need 3 decimal places, and we need to get it as close as possible to the 0 down here. So now we go to your table set. Keep track of this 9.5. So we're going to go table set. We're going to start at 9.5, and we're going to increment it to 3 decimal places, 0.001. I want to see the closest when it hits the ground. Now I go look at my table. I'm scanning down for my Y. I want to see when the Y gets the closest to 0. I couldn't do it on my graph anymore because it was incremented by 0.5. So just keep going down. Do you see it? So what's the time? What's the X value? To get your X value, watch what you have to do, guys. Oops. To get your X value, when you're here, scroll over to this X. Do you see it? Now you'll get, your calculator can't fit all those numbers into these little bars. So scroll over if you want the exact value. And then you're going to have to round this to 3 decimal places. So 13. There's your X. So it took you 9.521 seconds, and it went 1,306.012 feet away from you. Remember, we have to get 3 decimals. Now, here's the thing. You could set your T-step a little bit smaller. You could set your T-step just a little bit smaller. It'll cut down on the look of your table. But your graph goes a little bit slower. In this case, it's not so bad. You don't want to do this one into 0.001. It'll never, it'll take forever to get there. But once you're comfortable to where your T-step is, so you're going to trace, and now look, see my T-step is going in 0.3s? I'm not going that far, so this is not so bad. I'll get a little bit closer before I have to go to my table. See, it's taking me a little bit longer because my T-step is smaller. But from here, I'm really no closer because of the way it landed. So I usually keep my T-step at 0.5, and then I go to my table when I get close. Yes?
How come there's no option to find the intersect where it was
There's no intersect. There's no intersect in this, you know. No. You can't. Did you notice it? Second calc? There's no intersect. There's a value. I could at any time, and this is my T value. This is my time value. If I say, oh, at 3 seconds, where were you? Like, this is what physics does. And I take a snapshot. Right? Isn't this what you guys do? Like, at 3 seconds, where are you? if you want to know where your things are, horizontally, vertically. Don't you guys do this in physics? I did this in physics in college. Well, we never had a graphing I didn't even have a calculator, but we obviously didn't have a graphing calculator when the dinosaurs were roaming the earth. So, I mean, you could at any time say a value and get what your value is. Where am I at 9 seconds? I could even say this. Okay, I know I'm getting close. Where am I at 9.2 seconds? I'm getting closer. Oh, where am I at 9.25 seconds?
I think it's just easier to,
It's so much easier. Whoops, I went to the wrong one. It's so much easier to go to the table than this. See how long this will take me? This will take me a long time to get there. I mean, you can, but it's so much easier when you get within a reasonable amount. Then go to your table set, start at that p-value, and increment it to the 3 decimal places, to the thousandths decimals. And you want to put 0.001. So does this make sense?
yes.
Yeah? Okay, let's try another one. Don't do number 4 for homework, and just hold off on number 4. 4 we're going to do it another time. But go to number 5. Alright, this is a pretty cool one. We have a lot of, does this one have the golf ones in it?
Well, I was just in the wrong spot.
No.
It equals 354.
Oh, it does?
Yeah.
Okay, sorry about that.
Alright, you gotta go back up. There you go.
There we go. And the other, look at all the dots on this one. On the other one, we have ones that Mr. Nee did for golf. When Mr. Nee swings golf club and...
Number 2.
Oh, is there one for golf? Yeah, the other packet, though, I think it even says Mr. Nee. Okay, so we have an NFL punter at the 15-yard line. The ball is sitting there, and the guy comes to punt it. The ball is at the 15-yard line with an initial velocity. These are the things we have to remember. Of 85 feet per second and an angle of elevation of 56 degrees. So here's the field. Here's the 15-yard line. And he's going to kick this ball, and it's going to come back down and hit the ground somewhere. Now, here's my velocity, 85 feet per second. And I have an angle of elevation of 56 degrees. And I'm 15 yards away, so from the end zone, from the 0. Do we have any concerns right now? Okay, so let's start. So velocity, 85 t. Cosine of my angle. Right. Now there's a couple of ways we could work this. He's not at the 0, 0, right? Where's he starting? 15. So is that a horizontal movement or a vertical movement? Horizontal. So should I add 15? Okay. No. I should add it, but what's the problem here? What's my velocity in? B. B per second. What's my 15 in? Yards. So what do I have to add? 45. I have to take my 15 yards and multiply it into feet. What's my velocity in? Feet. Okay, so I'm going to add my 45. And there's a number of ways you can do this. You can subtract it at the end. You can do it in the beginning. I think this one's a little bit easier just because we're not starting at the 0. We're going to start here. And I want your diagram to show that. I mean, if you didn't put the 45, that's fine. You're still going to hang the same time in the air, but you're just going to come up the field a little bit, 15 yards sooner. So, but I think this one makes a better diagram. So now, we've got the sine of 56. Do we have anything else that's going to affect our our vertical movement? So don't forget to put your negative 16t squared. Don't forget to put that. All right, so now let's build this. See, aren't these fun? It's a little tedious, but use your table rather than your graph. So 85, don't forget the t, plus 45, don't forget to bring it back down. Okay, now let's go to our window first. How many seconds do you think this will take before it hits the ground? Is 0 to 12 a good amount?
I think we might do a little more.
Do you think it'll take 20 seconds to hit the ground?
Maybe.
Okay, we'll try 20. We'll try 20. Okay, now we're in feet. How many feet is a football field? It's 100 yards, right?
300.
So 300 feet. That's maximum. We know he's already started a little bit ahead of time, but how high up in the air do you think his ball will go? In feet. Oh, so 80. Let's go 100. You're only making the window, so you don't have to be exact, and we can absolutely change it if we look at your table. So now, we've got a perfect parabola. If not, then you do this, guys. You go to your table, you start at the 0, you increment by 1, and you take a look at your table. And you see, here's how many seconds it took for him to hit the ground. 4 point something seconds. See it? When y hits the ground? Okay, so now, go to your graph, and we want to know how far downfield will the football first hit the field. Now, I want to know this spot right here. Okay. There's a difference between how far downfield, if it's from him, how far did he kick the ball, or how far down the field did he start from the 0 and go all the way down. Hang time is the time in the air. Maximum height is up here. So let's do our maximum height, if that's good for you guys. Let's trace our maximum height. So we're going to trace as close to possible to that. Now, watch where we are. We're at times 2 seconds, and then we're away from it. That's 2.5. Yes, yes. And you can always go to your table and redo your window. Okay? So, again, we trace. We're between here and we're between here. Between 2 and 2.5, closer to 2. So, maybe start your table set at 2.2. See where you get at 2.2. And increment to the 3 decimal places. I'm looking for what? What am I looking for? What do I know that I'm going to see my highest point? What am I looking at? Which value? What, my y. Okay, I'm sorry. My y. And what am I going to look for it to do? And like, what am I looking for it to do? To start decreasing. I'm looking for it to increase. Look at this. They all look pretty much the same. So until you go over here, you can't really see if it's increasing, decreasing. Now, just go 1 down. See, you notice that it increased, right? So somewhere in here is going to be my answer. Your calculator can't get any more exact than that. And that's just the way it goes with that. Unfortunately, we're kind of like just having to go through. So here, and then it starts to go down. See it? So here is my answer. So my maximum height, my time is 2.202. This is for this one. And my height is, what did we say your height was? 77.90. We're rounding there anyway. The most important part on that was the time. Feet. Okay, so now we determined your maximum height. So your hang time, how long did it stay in the air? When we get to this, we'll see how long it stayed in the air. Now, continue tracing. Trace all the way through. Oops, what am I doing? Trace all the way through until, what am I looking for now?
When it goes under the...
Good, when this goes under the 0, I'm looking for, so I'm barely under the 0 here. So somewhere before 4.5. So maybe I want to set my table set to 4.5 and start looking. I'll just go up a little bit. I'm just going to go up until I find the 0. If you find that you're doing this for too long, then change your time. Change your start. Hold on, Mrs. Moore. Yes. He's right. Oh, and it wasn't that last year. Let me plug you back, okay? Okay, fine. They're changing our statistics course, Mercy Colleges. So if you find that this is too long to get there, change your table set. Maybe you don't want to start that far down at what did we start it at? 2.5? Oh, what did we start it at before? 4.5? 4.5, so maybe we'll want to start at 4.4. This is the annoying part, but see, here we are. Just change it up a little until you get close enough. Now, you're down here. Again, scroll over this because this is where your X is the furthest distance. They only have 2 decimal places. You need 3 decimal places. So your time is 4.404, and your vertical and your horizontal distance is, did anybody keep track of that? 254.328 feet. Now, that's feet. If you'd rather look at it in yards, when a person kicks a ball, they probably give you a yard measurement. How do I get back into yards? Divide it by 3. 3 feet to a yard. And then you'll get your yard measurement. Okay, but watch, because this happens a lot. Are we comfortable with this? It gives you something to kind of play with a little bit. What I do want to just make you aware of too is if you take a look at number 7, it works off of 6, but number 7 has a wind speed. So when you're doing this, the velocity came from up above. So let me just hit the velocity of 103. So when you're doing a wind speed, it's going to affect your X. So you have your 103. There's your velocity from number 6, because number 6, 7, and 8 all deal with the same thing. Here's your cosine of your angle. Now, your wind speed, if it's in the same direction, what's it going to do to your ball, or whatever this is going? You're going to have to add, right? The wind speed is in your direction. If it's in the opposite direction, what are you going to do? Subtract. The wind speed has to be in the same measurement as whatever your velocity is. So if my velocity is feet per second, my wind speed is feet per second, I'm good. I say plus 22 T. Don't forget to put the T on your wind speed. If the wind speed is miles per hour and my wind speed is feet per second, I have to convert that. So just be careful of that. And this is the opposite direction, you're going to subtract this guy. So don't do number 4. 6 through 8 are all kind of connected. So do 2 and 3. 2 and 3 are pretty good. Don't do 4. And do 6 through 8. we'll do forearm class together. It works a little bit differently. There's two things going on at the same time. They're throwing the ball to each other, so I'd rather like have you not go crazy. I'll do it with you. It's a little bit tedious, but work your calculator and then work your table as well. Don't do everything from the graph. Yep.